In this video, we're going to take a look at a bunch of improper integrals and how to evaluate them, and if they're either convergent or divergent. In part A, we have the definite integral from 4 to infinity of 1 over 7 to the power of x dx. Now, what makes this an improper integral? Improper integrals arise whenever you have a definite integral involving infinity or negative infinity, or a number that causes a discontinuity in the function itself. So in part A, we have infinity being involved. And you can't really plug in infinity, so we're going to have to change up this notation a little bit and turn it into a limit, and we can call infinity some other variable, and we'll see what happens as that variable approaches infinity. And we're also going to be taking the definite integral at the same time. So we can go ahead and call infinity some other variable such as capital T. And so I can change this to 7 to the negative x dx first. And then we can say that this is equal to the limit as t approaches infinity multiplied by the definite integral from 4 to capital T of 7 to the power of negative x dx. And so now we can evaluate this integral. We can say that this is the limit as t approaches infinity. And to find this antiderivative, all we have to do is just do a guess and check. So if we were to take the derivative of this right now, we would get 7 to the negative x multiplied by the derivative of the inside, which is the exponent, multiplied by ln of the base. And as you can see, here we do not have a negative sign out in front, and neither do we have a ln 7. So in order to compensate for that, we need to divide by negative ln 7 here. And this will be evaluated when x is equal to t and when x is equal to 4. And if you don't believe me, take the derivative of this and you're going to get back to here. And because we're going to be plugging in infinity, I'm just going to take this 7 to the negative x and use the fact that this is equivalent to saying 1 over 7 to the x. And I'm going to pull that into the denominator. And I'll bring this negative out in front. So I'm going to say that this is equal to the limit as t approaches infinity of 1 over ln 7 multiplied by 7 to the x with the negative out in front. And this will be evaluated when x is equal to t and 4. And so we can now say that this is equal to the limit as t approaches infinity of negative 1 over ln 7 multiplied by 7 to the power of t minus, so I'm just going to change it to a positive 1 over ln 7 multiplied by 7 to the power of 4. And so now I can go ahead and simply plug in t as infinity. So we can say that this is equal to 1 over ln 7 multiplied by 7 to the power of infinity plus 1 over ln 7 multiplied by 7 to the power of 4, which is 2,401. And so in the denominator, what we're going to get is infinity. And so what we end up getting here is some small number over a very big number. And so really, this is just going to approach 0, which just goes away. And so our final answer is going to be 1 over 2,401 ln 7. And as you can see, we got a finite value here, and therefore we can say that this is convergent. Moving on to part A, we have the integral going from 4 to infinity of 3 over x to the 1 over 7 dx. First, I'm going to rewrite this in a different way such that we can find the antiderivative more easily. So I'm going to change this to 3x to the negative 1 over 7 dx. And like before, we can call infinity some other variable such as t, and then take the limit and see what happens as it approaches infinity. So this is equal to the limit as t approaches infinity multiplied by the integral going from 4 to t of 3x to the negative 1 over 7 dx. Now to evaluate this integral, we can use a simple power rule of integration where we know to just add 1 to the exponent and then divide by that exponent. So we're going to do that right here. So this is equal to t, the limit as t approaches infinity, multiplied by 3 times x to the 6 over 7 divided by 6 over 7. And this will be evaluated between 4 and t. However, dividing by 6 over 7 is also the same thing as saying multiplication by 7 over 6. So why don't we get rid of this ugly looking division and do that instead? And I'm also going to multiply the 7 over 6 with the 3 we already have out in front, which is going to give us 7 over 2. And so now we can say that this is equal to the limit as t approaches infinity of 7 over 2 t to the 6 over 7 minus 7 over 2 times 4 to the 6 over 7. We can now plug in infinity and see what happens. We get 7 over 2 multiplied by infinity to the 6 over 7 minus 7 over 2, 4 to the power of 6 over 7. As you can see, we now get infinity minus some number, some finite number, which is equal to infinity. And as a result, our final answer is not a finite number. It is infinity. And so therefore, we say that this is divergent. Now what about for part C? In part C, we have the exact same thing. However, in this case, the integral goes from 0 to 4 of 3 over x to the 1 over 7 dx. I'm going to go ahead and look at what's causing an issue right now. And I see if I plug in 0 into my denominator, I'm going to get 3 over 0, which we're not allowed to do. You cannot divide by 0. So that's what's causing the issue right now. So we can call 0 some other variable such as t and see what happens as t approaches 0. But the question is, will t approach 0 from the left or the right? Well, if you have trouble thinking about this, just draw a number line. And then over here we'll have 0. And over here we'll have 4. And the only way to approach 0 is to approach from the right side. And so we'll say 0 from the right. And so this is the same thing as saying the limit as t approaches 0 from the right multiplied by the integral going from t to 4 of 3x to the negative 1 over 7 dx. And then from the previous part, we already know what the antiderivative is, which was 7 over 2 x to the 6 over 7. And in this case, it will be evaluated between t and 4. So let's go ahead and do that. This is equal to the limit as t approaches 0 from the right of 7 over 2 multiplied by 4 to the power of 6 over 7 minus 7 over 2 multiplied by t to the 6 over 7. And do not make the mistake of thinking you can cancel out this 4 and the 2 to reduce it to 2 over 1. Because this is an exponential function, and we cannot just reduce them like it is. I would just keep it like this if I were you. So we can say that this is equal to 7 over 2 multiplied by 4 to the 6 over 7, and then minus 7 over 2 multiplied by 0 to the 6 over 7. As the final answer, we get 7 over 2 multiplied by 4 to the 6 over 7. And as you can see, we got a finite value for our answer. And so therefore we say that this is convergent. What about part D? In part D, we have the integral going from negative infinity to 4 of 7x dx. I look and see what's causing an issue right now, and because of the infinity, this is an improper integral. We can call this some other variable such as t and see what happens to the limit as t approaches negative infinity. So we can say that this is the limit as t approaches negative infinity multiplied by the integral going from t to 4 of 7x dx. Now this integral is very easy to evaluate actually. So we can say this is the limit as t approaches negative infinity of 7 over x over ln 7. And how did I know to divide by ln 7? It's because if you take the derivative of 7 to the x, you're going to get 7 to the x multiplied by the derivative of the exponent multiplied by ln of the base. And as you can see here, we do not have ln 7 here. So in order to get rid of this ln 7, we need to divide by a ln 7. And if you don't believe me, just take this derivative and you're going to get the exact same thing that is here. And so this will be evaluated between t and 4. So this is equal to the limit as t approaches negative infinity of 7 to the power of 4 over ln 7 minus 7 to the power of t over ln 7. And so I can go ahead and plug in t equals negative infinity now and see what happens. We get 7 to the power of 4 over ln 7 minus 7 to the negative infinity over ln 7. And so this is actually the same thing as saying 1 over ln 7 multiplied by 7 to the infinity. And so this is going to lead to us getting 1 over infinity, which is going to approach 0. So really, this will just go away. And then we're going to be left with a final answer of 2,401 divided by ln 7. And as you can see, we got a finite answer for our answer. And so therefore we say that this is convergent. What about part E? In part E, we have the integral going from 0 to 9 of e to the 1 over x divided by x squared dx. But right now I see we have a 0 here, which is going to cause some issues because if you plug in x equals 0, you're going to get division by 0, which is not allowed. And so in order to fix that, we'll have to call this some other variable such as t and see what happens as t approaches 0. But from what side? Well, once again, just draw a number line. And so if 9 is over here and 0 is over here, the only way to approach 0 is to approach from the right. And so I also noticed that if I'm going to eventually take the integral and evaluate it, this x squared in the bottom is causing some issues. And so what I'm going to do is I can use u substitution and set u equal to 1 over x to get rid of this x squared. Because if I take the derivative of 1 over x, I'm going to get negative 1 over x squared. And then if I solve for dx, I'll be able to nicely cancel the x squared in the denominator. So let's go ahead and do that. We can say that u is equal to 1 over x, which is equal to x to the negative 1. And then solving for the derivative, we get du is equal to negative x to the negative 2 dx. Solving for dx, we can first rewrite this as negative 1 over x squared dx. And then finally solving for dx, we get negative x squared du is equal to dx. And so I can now take this dx and plug it into here and then cancel out the x squared. For now, I'm just gonna drop the definite integral with the numbers for now and just do this aside. So I'm gonna say that this is equal to e to the 1 over x divided by x squared. And then I'm gonna replace dx with what we just solved for, which is gonna be x squared du. And because we said that 1 over x is equal to u, I'll just change that as well. And so this is going to be equal to, we see that the x squareds nicely cancel out, and we're left with the integral of e to the u multiplied by negative du, which is equal to the integral of negative e to the u du. And this antiderivative is just equal to negative e to the u and plus c at the end. But for our purposes, we don't need the plus c because we're going to be evaluating this with numbers, and the c's are just going to cancel it anyway. So leaving this to the side, let's go ahead and evaluate this. So what I'm going to do is I'm going to replace u with 1 over x. And so this is going to be the limit as t approaches 0 from the right, multiplied by negative e to the 1 over x, which will be evaluated between t and 9. And so we're going to get the limit as t approaches 0 from the right of negative e to the 1 over 9 minus, which I'll just change to a positive, e to the 1 over t. And so we can now go ahead and directly substitute in t equals 0 and see what happens. So we're going to get negative e to the 1 over 9 plus e to the 1 over 0. And as you can see, here we're going to get e to the power of infinity. Because recall that it's going to be a relatively big number divided by a very, very, very small number. And that's going to approach infinity. And so that means that e to the infinity is also equal to infinity. And so this is just negative e to the 1 over 9 plus infinity, which is the same thing as saying infinity minus a number. And so that's just equal to infinity. And so notice how we got a non-finite number, and so therefore we say that this is divergent.